This is a video documentary showing the energy and water consumption levels for the Heriot Watt University Dubai campus building and our suggestions to make it better.
Heriot Watt University Dubai campus is located in Dubai International Academic City. It consists of two blocks, the academic block and the residential block. The first block consists of 3 floors with multiple classrooms, mechanical, automotive, civil and electrical engineering labs. IT labs, 1 library, and fashion and interior design studios are also located in this block. It also includes outdoor sport facilities like basketball, football, and tennis courts. The second block consists of an auditorium, recreational room, a food court, gymnasium, quiet study area, and both male and female student accommodation. The first building is accessible from all 4 sides of the building, and the circulation is simple and formal, with a central corridor that passes through from one side of the building to the opposite side. There are 2 main entrances into the university, mainly the vehicular entrance and the pedestrian entrance.
The following table shows the obtained experimental values using lab equipments from the civil engineering lab. Lab equipments were used to obtain the readings in different areas of the university as seen in Table 1. A LT10 light meter was used to obtain the readings of light intensity. A SL10 personal sound level meter was used to measure sound levels. A HT30 heat stress meter was used to measure temperatures, and a CO2 analyzer for humidity and air quality. As seen from Table 1, the temperature is found to be higher in the left and the right hand side of the university building for all the floors and is less in the middle section of the building. This is due to the presence of glass facades in the left and the right sides of the building, which increases the amount of solar heat gains entering the building. The benchmark values for the temperature is between 23 degrees Celsius and 25 degrees Celsius. The temperature of the left and the middle section for all the floors of the building fall within the benchmark range, but with the temperatures recorded in the right side of the building is higher than the benchmark range. This is due to the position of the sun, as the right side of the building was facing the sun when the readings were taken. The interior illumination levels benchmark is at 300 lux or greater, and it can never go less than 300 lux. The light intensity of the middle section of the building is found to be less than 300 lux for all the floors. The left and the right side of the building has approximate levels of light intensity, as the illumination levels are much more than 300 lux. The right side of the ground floor has an illuminance level which does not fall within the benchmark range, as the light intensity is 90.5 lux. The light intensity in the outer area towards the right side of the building is found to be 450 lume, where the light intensity towards the left is found to be 20,200 lume. This is because the right side of the building was facing the sun when the readings were taken, and therefore has a greater light intensity when compared to the other side.
The relative humidity is higher in the right and left side of the university building when compared to the middle section of the building. This is due to greater amount of solar heat gains which enters the building through the glass facades. As seen from graph 1, the topmost floor has an increased percentage of relative humidity when compared to the other floors, with the ground floor having the least. Therefore, it can be concluded that the solar heat gains from the glass facades present in the topmost floor is much more when compared to the other floors present in the building. The benchmark for air quality is below 880 ppm. Air quality is basically the degree to which the air in a particular place is pollution-free. Therefore, if there is an increased value for the air quality, CO2 content present in the air is more. As seen from the graph 2 below, the average air quality ppm for the ground floor and the first floor falls within the benchmark range. The second floor has an air quality value of 1,259 ppm, and the third floor has 1,169. The air quality in the second and third floor is much more than the benchmark value, as there are staff rooms and a lot of classrooms, and therefore these floors are occupied with people throughout the day, which in return increases the carbon emissions. The benchmark for the sound level is equal to or below 25 decibels. The first, second, and third floor has sound level close to 25 decibels, which is the benchmark value. It can be evidently seen from graph 3 that the ground floor has a sound level of 72 decibels, which is much more than the benchmark value. This is because the reception present in the ground floor is crowded during the daytime, which leads to an increase in the sound levels, as seen in the graph shown below. The total energy consumption of the building in 2013 is calculated to be 1,065,989 kilowatt hours, and the total water consumption is calculated to be 3,874,000 gallons, as it can be evidently seen in Table 2. The energy consumption is at the peak during the month of September and least during December, as seen in graph number 4. September experiences summer, and solar heat gains through the walls of the building will be greater during this time, and therefore lots of energy is being used to maintain thermal comfort using the building, whereas energy consumption is less during December, as the outdoor temperature is usually moderate or cold, and indoor thermal comfort can be easily maintained. The water consumption for 2013 is higher for September, which is 674,000 gallons, and less for the months January and March, which is 500 gallons, as seen in graph 5. Active and passive design strategies. Passive design strategies include ideas that are focused on the design of windows, materials used in the building, and walls and floors to collect and distribute required amount of solar energy into the building, which as a result would reduce the total energy demand of the building. Passive design strategies will be helpful in reducing the building's reliance on mechanical and electrical systems to heat and cool the building. Some of the strategies are orienting the building in response to sun path, shading the building by introducing shading devices, using materials with favorable thermal mass properties for the climate, designing the interior spaces of the building to assist in effectively heating and cooling the building naturally, using double or triple glazed windows which would limit the amount of heat and light that enters the building. Active design strategies. Active design strategies use purchased energy to keep the building comfortable. These strategies include forced air HVAC systems, heat pumps, radiant panels or chilled beams, and electric lights. Active solar technology is the only strategy that can be implemented in the Heriot Watt building, as other options like wind, hydro, and geothermal are not feasible due to the orientation and location of the building. Active solar technology uses equipment to convert solar energy into usable electricity or to heat water for process or domestic use in the building. These technologies are steadily evolving and their efficiency is improving rapidly. The procedure for installing this technology includes designing areas ideal for photovoltaic panel arrays. Trees, mechanical units, and other buildings should not shade the panels at any time. Determining the optimal solar panel installation angle. Panels typically produce the most energy when tilted at an angle equal to the latitude of the sun at that specific location. Installing an energy dashboard for tracking and displaying the array's performance. The energy dashboard also educates the building occupants on how their behaviors impact building performance. As seen from Figure 1, solar panels are tilted at an angle of 42 degrees during winter, 65 degrees during spring and autumn, and 88 degrees during summer for them to work efficiently in generating electricity. In Graph 6, energy generated per month in kilowatt hours and average daily energy by month in kilowatt hours per day is shown. This graph shows the breakdown of energy by month, and the total energy generated by the solar panels for 1 year is calculated to be 69,085.85 kilowatt hours. Kyocera KD180GXLP is the panel model used to generate electricity, and the size of each panel is 39 by 52 inches. A total of 150 panels will be installed on the roof of the Heriot Watt building. estimated cost is known to be $108,108, and the cost of electricity in a year is $8,294. Using this information to calculate the payback period, which will be the estimated cost divided by the cost of electricity generated by the solar panels in a year, the payback period will be calculated to be 13 years.